Okay, so you'll see the properties of limits up here. Just about any of the normal operations, addition, subtraction, multiplication, and division can be done with limits. In other words, if you want to calculate the limit as x approaches a of one function f of x plus another function g of x, it's the same as calculating the limit of f of x separately, g of x separately, and adding those two numbers together. That's assuming that each of those functions has a limit at that number. So limit, remember, a limit is just a real number. That's all it is. It's a real number. And it's the y-coordinate of what you get when you plug x in if the function is defined. If the function is not defined there, you have a hole, for example, then it's what it would be if that hole were part of the graph. So it's kind of the weird part of it. So what this is saying is that limit of the sum is equal to the sum of the limits. Limit of the difference of two functions is equal to the difference of the limits. So you could calculate each limit separately and subtract them. And the limit of the product of two functions is equal to the product of the limits. And the limit of the quotient of two functions is equal to the quotient of the limits, as long as the limit of the bottom one is not 0. And remember, it's okay to have a limit of 0. 0 is a real number. So as long as the limit of the bottom one is not 0. And then if you have the limit of some constant scalar, we call this a scalar multiple of the function, it's equal to the scalar multiple times the limit of the function as x approaches a. So what that's really saying is that the normal operations you can do with adding, subtracting, multiplying, dividing functions works with limits of those functions as well, which is nice. Okay, today so here's our learning objectives. Our learning target is I can use substitution, algebraic techniques, or tables, or I could say on here graphs, to calculate a limit. Yesterday we started with tables and graphs, but we were just looking at pictures or looking at our tables. Actually, we started tables last week on those activities we did. But oftentimes we can calculate the limit using algebraic techniques or something as easy as substitution. Direct substitution is just plug in the number and get an answer. Try that first. So plug in a number and get an answer. If that works, we're good to go. You found the limit. The limit, remember, is just the y value of that function. Now, if you plug in the number and you don't get an answer, then you've got to use some other technique. Okay? So if you plug in a number and you get a 0, say, in the denominator, then you've got to find the limit another way or prove that the limit does not exist. Okay, these next two techniques are algebraic techniques that involve doing some type of algebraic simplification and then going back to direct substitution. So it's one of those things where if you directly try to substitute and things go badly, don't try to do that again unless you made an arithmetic error. But assuming you didn't make an arithmetic error, if it doesn't work to just plug it in, then you want to use one of these algebraic techniques. So maybe factor and reduce. So this is one of those things where you could be asked to use anything you've learned in algebra up to this point in terms of factoring. Factoring could be a GCF factoring, difference of squares, perfect square trinomial. Maybe some of you learned the factoring by FOIL method, factoring by X box method, perhaps. It's actually factoring by grouping. Any of the methods you've learned. Okay, it could be cubics. This is where it gets difficult because the algebra that you're asked to do to simplify these before you find the limit can be difficult. What's just so broad? It could be anything. The other method is rationalizing, and there are other methods as well, but multiplying by I'm going to put in quotes, a conjugate form. We're not really dealing with complex numbers here. We're dealing with real numbers and functions in the real number field, but you might be asked to multiply by a conjugate to get rid of radicals. I'll show you what I mean by that. So those are the techniques to solve limits. So we're going to try some of these out. This first few will be pretty easy. First several. Okay. You know, what is limit stuff about if it's that easy? Okay, so what's the first thing we try here to find the limit? Plug it in. Guys, what kind of function is this right here that we're finding the limit as x approaches 4 of? Parabola. So all we're doing is plugging in 4 and asking what is the output at 4. So it looks like this. Just plug in 4, we square it, and we get 16. So we're literally plugging in 4 for x. What about this one? Yeah, it's -10 is the limit. That's just a linear function with a slope of 5 and a y-intercept of 0. This is a trigonometric function. It's going to look like this. Pi cosine pi. So I've got pi, and cosine of pi is equal to, oh, here's unit circle stuff. Good review. It's -1. So this is negative pi. Okay, and then d. Just plug it in here. 4x. By the way, in your textbooks, this is chapter 12, section 2. We did section 1 yesterday. 1 plus 1 is 2. 2 minus 6 is -4 over 3.
So -1.
Oh, is it? Okay. Yeah, I can't see it. That's why I grabbed this sheet so I could see it. Yeah, my little subscript and superscripts don't show up on here, so you have to pay attention to your sheet. I'm going to have to look at it too. You're right. It's -1 squared plus -1 minus 6 over -1 plus 3, which should equal, I got -3. So there we go. All right, now, I'm going to just demonstrate what happens here first. This is the, quote, problem spot. We plug in -3. Everywhere we see an x. And we get 9 minus 3 is 6, minus 6 is 0 over 0. We call this an indeterminate form. So that's an indeterminate form. That's E on the end of that. And what that says in normal language is we cannot determine what the limit is. It doesn't say there is no limit. We just can't determine what it is. Okay, based on that. So that's when we kick into one of those other two steps. Is there another way to rewrite this so that we can cancel something out? If you can't cancel something out or simplify this in any way, don't expect to get a different result, right? But if we can, see, this goes back to the idea of a hole is called a removable discontinuity. I think we talked about that before. And those can be found out by noticing what cancels from bottom, right? The hole is what cancels out from the bottom and makes the bottom 0. So we go back to the drawing board here and have to ask ourselves, can I rewrite this limit in some way? So the limit as x approaches -3 and I'm expecting to be able to factor that top part. What are the factors of that top quadratic? X minus 2 and x plus 3, that's right. So now I have a new limit expression that's different than when I started. So I can expect a different result. So limit as x approaches negative 3. The x plus 3's cancel out. Now we know that that just means that's a hole in the graph. What I'm left with is the equation x minus 2, which we know from our algebra is a linear function, a slope of 1, going through negative 2. If I were to graph this, it would look like this. Y-intercept of negative 2, slope of 1, so 1 up, 1 over, 1 up, 1 over, and it just so happens, because if I go down 1, left 1, down another 1, left 1, down another 1, left 1, at negative 3, so right here at negative, x equals negative 3, I would have a hole in the graph. So if you plug this into your calculator, unless you have the color one, it won't really show up, but you will have just a line with a hole in it. With the color ones, you can kind of tell that there's a hole there. So we learned from our little activity that yes, we can have a limit where there's a hole in the graph. That's not a problem. And so let's find out what that limit is. I think this will make sense. If I want to find out what that limit is, I just have to find out the y-coordinate of that hole. How do I find out the y-coordinate of this hole besides? You could count, yeah, but you can find it easier by plugging in, I think. So it's negative 3 minus 2, which is negative 5. And so my limit is negative 5.
Jonah and Holly.
I'll take it. Oh, that's so nice of you. Jonah and Noah.
I've never confused them.
Finally got to the W's. Just
Wait, Joe's on you?
supposed
But
to.
I'm a W too.
You are.
My middle name is Wayne.
Say.
What else?
All right. Now, I like you guys to try F. Plug in 1, you could just do it in your head and maybe don't write too much down. Because guess what
The
happens?
top is zero.
Top is 0,
Yeah.
bottom 0.
And the bottom stuff is
So what does that mean?
All real solutions.
Can I show you what?
With legend.
Yeah. Just, so if I plug, you might not want to write this down though, because we're in that room. But if I plug in 1 on the top, you see that it equals 0, right? If I plug in 1 on the bottom, it's 1 minus 1 is 0, plus 1 is 1, minus 1 is 0. I get 0 over 0. That's the first step. That tells me I've got to go back to the drawing board, right? I have to do some kind of simplification. Now, here's the cool thing about this. Here's the cool thing about this. Yes, it's a cubic on the bottom. We did learn how to factor cubics. But I've got a little bit of a hint here. If anything is going to be different, what would need to go away?
X minus 1.
So what does that tell you? One factor of that cubic on the bottom might possibly be probably x minus 1. So, go up to my little scratch space up here. Let's assume that x minus 1 is a factor, okay? If it's not, we'll know when we do our synthetic division. Uh-oh, synthetic division, remember that?
Oh, no.
This is such good review. So, okay, let's back up a little bit here. What are the possible zeros of this function based on the rational root theorem? 1 or negative 1. That's it. They're combinations of the first and the last term. So you take, it's plus or minus 1 over plus or minus 1. It's actually plus or minus p over plus or minus q, where this is my p, this is my q, the coefficient over there. So it's plus or minus all the factors of the constant last term over plus or minus all the factors of the first term. But like I said, I wouldn't expect anything different to happen unless x minus 1 gets canceled out. So I would guess, using my super reasoning skills, that 1 is a 0 of that polynomial on the bottom. So let's do our synthetic division up here in our scratch paper spot up here. We're going to divide 1 into 1, negative 1, 1, negative 1. So I'm writing down the coefficients of each of these. This is such good review. I'm going to ask you to do this like a final. So bring down the 1. And this is the type of thing that pops up in calculus. You're just expected at any time to be able to do any of the algebra you've learned to simplify expressions for the purpose of doing calculus with them. So bring down the 1. 1 times 1 is 1. That's 0. This is positive 1. It does work.
Wait, it does.
It does work. Because it's 0 right here. So what does that tell me? How does this factor? So the limit as x approaches 1 of x minus 1 on the top, and on the bottom is x minus 1 times x squared plus 1. So you guys watching carefully as I'm doing the factoring. Okay? Do you remember the synthetic division? Handle that? Do you remember, why did we think that 1 might be a 0 of this? Do you remember that? It's on the top and we want this to change somehow before. If we want to expect anything different to happen than 0 over 0, we want that x minus 1 to cancel out. It cancels out, right? So we're left with a new expression. Limit as x approaches 1 of 1 over x squared plus 1. Now plug in 1. Do you get something other than 0 over 0? You get 1 over 2. So what's the limit? 1/2. So if you get an indeterminate form, 0 over 0, expect a factor, cancel something, and re-plug it in. And if after you factor nothing cancels, then you gotta go look at the graph. Okay, that's the only other method to look at the graph. Okay, at least algebraically speaking. All right, G. Guess what happens on G if I plug in a 0? Can you do it? 0 over 0, yeah. So you have to. This is the hardest one for most students. You have to watch this carefully. This goes back to the idea of dividing complex numbers. When you divide a complex, don't write this down yet. When you divide a complex number like 3 plus I divided by 2 minus 3I, you remember what you would do to do this division? It's got a special name. Yeah, it's called the conjugate. And so division becomes simplification, if you will, to get rid of the I in the bottom. Okay, that's all it is. So this is called multiplying by the conjugate. It's something you've done before for the purpose of dividing complex numbers. We're going to do it now for a different purpose. The purpose now is to rewrite this expression with a radical in it. Yeah, Matt.
Where did you get the 3 from? The 3 plus 3?
Oh, it should be 2. Sorry. It would need to match the bottom but have a different sign. Yeah, good point. That's called multiplying by the conjugate. So, with that in mind, what do you think the conjugate of this top expression might be? It's kind of the same form.
X plus 1 plus 1?
Yes, that's right. That's right. It's of the same form, so it's x plus 1 is the conjugate. And here's the thing. We don't want to be rule breakers, right? You guys are compliant folks. That's, you like rules. They help us to. Yes, accept dumb rules. So to avoid breaking any rules, we have to multiply the same thing on the bottom. Otherwise, we're changing the original problem. Right here, I'm being super smart here. I'm multiplying by a very well or carefully chosen value of 1. Right? Probably not the one you were thinking of. But this is just multiplying by 1, which we know by the identity property of multiplication doesn't change it. Right? So this is the trick that we're going to use to get rid of the radical and rewrite this expression so we don't get an indeterminate form. It really will work. Watch this. So it's the limit. Here's the new expression. As x approaches 0. Okay, this is a difference of squares form, believe it or not. In a difference of squares, the middle term cancels out. So we can be smart about this and just square the first term and square the last term. If I square the first term, what do I end up with? Sx plus 1. And if I square the last term, I just end up with a 1. Yeah, so actually I'm not squaring the last term, I'm multiplying. So it's x plus 1 minus 1. So what happens is the middle term cancels out. All I'm doing is multiplying the first terms, that's a better way to say it, and multiplying the last terms. All over x times all this garbage. And I would not distribute the x by all that garbage. I would just leave it like that. Here's why. What's that? It's possible you could rewrite it, but we don't need to. We're going to plug in a number, so it won't matter. These cancel out. Changing, so would you agree that I have a different expression? It's a simplified expression. I just took out the ones, right? So it has changed. Also, I could take out the x's. So what I have here is limit as x approaches 0 of 1 over this mess. Square root of x plus 1 plus 1. So the square root sign is over this. Let's fix this up. Alright, so do you see the square root sign is over the x plus 1, and then I have a plus 1 there. So the 1's cancel out, the x's cancel out to equal 1. Two different types of canceling, right? And then I plug in 0. So when I plug in 0, what do I get here? Plug in 0 right here. 0 plus 1 is 1. Square root of 1 is 1. 1 plus 1 is 2, so it's 1/2 again. Yes. So the limit of that function is also 1/2. All right. As you can imagine, the rest of these all end up being indeterminate forms. Okay. So each one of them requires you to use some kind of algebraic trick. I'm going to demo. These are each algebraic tricks you've seen before, but I'm going to demo each of them, and then I'll let you practice in groups. Okay. I think it'll be helpful to work together. Okay, so here we go. We're going to go through the rest of these fairly quickly. All right. So did you catch that? It said every one of the rest of these will equal 0 to 0. Okay. Just have to try. You can check it. Okay. They all require an algebraic trick, and I'm going to demo those to you. So you have to add each of these to your repertoire. Do you recognize this? They are perfect squares, and they're separated by a difference, or a minus sign. So how does it factor? What's the square root of x to the 4th? Okay. So it's, let's just do some factoring up here. It's x squared minus 4, x squared plus 4, you with me? Over x minus 2. Now nothing matches yet, but how does x squared minus 4 factor? Yeah, x minus 2, x plus 2, and I still have the x squared plus 4. All over x minus 2. So I cancel out the x minus 2's. That gives me reason to believe something different will happen when I go to plug in 2. Looks like it's a positive 2. So go ahead now and plug in 2 everywhere you see an x. So we have 2 plus 2. And then 2 squared plus 4. And that does equal 4 times 8, which is 32. So the limit of that function is 32. So what feature would this graph have at, well, let me back up. Let's see if you can answer this first. What kind of function would this be? Do you know what the parent graph would be of this function? It will be wavy. You could be more specific though. How many waves will it have? Up to 2. This is actually, when I look at this, guys, here's what I see. Forget about all this stuff. Doesn't matter as x gets bigger. X to the 4th over x to the 1st is x to the 3rd. So I'm seeing this as this thing would be a cubic, more or less. Especially as x gets bigger. And we have a hole at 2 comma 32. Okay. All right, the next one. Next one. Any ideas on what we could do to rewrite this next one before we factor it? Any ideas? What's that? Time. 5. No. Don't do that. It is, but what would your Algebra 1 teacher have told you, guys, if you had a negative coefficient of the x squared term of the a squared?
Make it unnegative.
Make it unnegative, right? How do you make it unnegative? What's the trick? Divide by -1 or pull out a -1. Yep. It just happens. So we'd have -1, and it would change all this around. 3a squared plus a minus 2 over a plus 1. So plugging in a -1, it looks like. So the limit. Okay. So the limit is a. The limit as a approaches -1 of. Now we have a new expression. Let's figure out the new expression. It's a negative something times something, and I'll bet one of those somethings is an a plus 1. No? I'll bet one of them is an a plus 1. Otherwise, nothing will change. So it's 3a and a plus 1. What's got to go with 3a so that I get a -2 as the last term? Probably -2. Does that work? Check it. Outer product is 3a. Inner product is -2a. Does that add to equal the middle term? Okay. So we've got it. A plus 1's cancel out. What's the limit as a approaches -1 of this thing that's left over? Well, it's -3. Let's go ahead and plug in the -1 now. What in the world is that? See, -3 minus 2, -5, -5 is +5. So yet another factoring trick here. We factored out a -1, and then went ahead and just factored that using FOIL. On J, you mean? Well, yeah, I know this was everybody's favorite from earlier. We did do, these are called complex fractions. So, what do you think we need to do with that complex fraction before we can cancel anything?
Probably more complex.
Yeah. Make it, yeah, basically make it not a fraction over a fraction. Make it into one fraction on top and another fraction on the bottom, not fraction minus a fraction over or something. So we're going to rewrite this by finding the common denominator. So what do I need to multiply 1 over x plus 3 by? And what do I need to multiply? Okay, 3, yep. What do I need to multiply 1 over 3 by? Not 3. Minus sign in between. I want the lowest common multiple here of x plus 3 and 3, which is going to be 3 times x plus 3. So I got to multiply the 3 by, well, a very carefully chosen one. It's x plus 3 over x plus 3. So I'm multiplying 1 over 3 by x plus 3 over x plus 3, and 1 over x plus 3 by 3 over 3. And then I don't forget the bottom. That's all over x. So the limit as x approaches 0 of 3, distribute the minus sign here, minus x minus 3 all over x plus 3 times 3 all over x. And I'm going to do, I'm going to write this as x over 1 because ultimately I'm going to multiply by the reciprocal of the bottom. Now, these cancel out here and here. So I'm left with the expression limit as x approaches 0 of negative x over 3 times x plus 3. And I'm going to multiply that by the reciprocal of the bottom. Here's the bottom. So the reciprocal of what I just circled would be 1 over x. Unfortunately, you guys don't have to extend the page option, do you? But I can just keep going. So these cancel. And now I'm ready to plug in the 0. Something has changed, right? I got rid of these. So it has changed. I can expect something different to happen at 0 over 0. So plug in 0 here. I've got negative 1 over 3 times 0 plus 3, which is negative 1 9. And that's our limit. So we've seen a difference of squares, a factor out of negative 1, a multiplied by the conjugate, a factor of cubic, complex fraction. You've seen about everything that we studied through the pre-calculus course. Here's one more. One more good algebraic technique. How do you expand this 1 plus h to the 4th out? Remember how to do that? Yeah, that's the most efficient way. It's the binomial theorem. That's what that triangle does. Is it? So, if you'd like to, you can multiply this by itself 4 times. We probably want to stay away from that, and maybe use Pascal's triangle to figure out the coefficients. So I go down to the 5th row, which has a 4 as the coefficient of the second term. Okay, this tells me, actually this 4th power up here tells me which row to use. So I go down to the 1, 4, 6, 4, 1 row. There's actually a way to calculate this using combinations on your calculator, but if the power is not too high, it's not a big deal to just go use Pascal's triangle to figure out the coefficients. So, expanded out version of this thing, let's write it down. It's limit as h approaches 0 of, okay, 1 h to the, do you remember how this starts? Actually, you can think of this as h plus 1 or 1 plus h. I'm going to think of it as h plus 1, so I'm going to go from h to the 4th down to h to the 0. If you thought of it as 1 plus h, you'd go from 1 to the 4th down to 1 to the 0, and the h's would come out. Okay? But it goes like this: 1h to the 4th, 1 to the 0, plus h to the 3rd, 1 to the 1st. Okay, here's how this works. If you think of this as h plus 1 to the 4th, the powers on the h start at 4th and go down, and the powers of the 1 start at 0 and go up. I don't know if you remember that, but you have two terms with the binomial theorem. So 1 to the 0 is still just 1. And we have plus h squared 1 to the 2nd plus h 1 to the 3rd plus 1 to the 4th. And then we have minus 1 because of the minus 1 up here on the top. So that's all over h. So let's clean this up a bit. We have the limit as h approaches 0 of 1 plus h to the 4th expanded out, which is h to the 4th plus h cubed plus h to the 2nd plus h plus 1 minus 1 all over h. Nothing has canceled out yet. Yeah. Oh, I didn't. Sorry, I goofed. So I'll do it in red here. 4, 6. I was concentrating so much on the powers. And then this would be 4. So go ahead and add these in, please. And then this would be 1 again. Thank you. So down here I would have 4, 6, 4, and then, of course, 1. That will make a difference in my final answer. Now, nothing is canceled out yet. But here I have a positive 1 and a negative 1. That cancels out. That's a start. What else is going to cancel out up here? So limit as h approaches 0. What else will factor out and then cancel out? Do you see it here? H, I can pull an h out. I'm left with h to the 3rd plus 4h squared plus 6h plus 4 all over h. So it's going to simplify even more. The h's cancel out. Without the canceling out of those h's, if I tried it right here, plugged in 0 for h, it'd still get 0 over 0 in determinate form. So that would tell me I haven't simplified it enough to be able to evaluate the limit. Now, though, I can plug in 0. If I plug in 0 here, here, and here, those first 3 terms are gone, and I'm left with 4 as my limit. So it's kind of similar to what we did with the difference quotient at the beginning of the year.